is our periodontal grid. So here I am defining how our neighborhood structure is built. So if you consider this particular site this is a tooth, and then there are 6 sites for every tooth that I'm measuring. If you consider this particular site, then the neighbors would be this particular site and this one. If you consider this one or like this one, then the neighbors would be this site, this one, and this one. So we modeled the adjacent sites of the same tooth and sites that share a gap between the teeth as neighbors. So for every site, there can be either 2 neighbors or 3 neighbors in my framework. 2 when you are considering this one, and then when they're in the gaps, like in here, there is one more that is contributed from here. These are the 3 types you can think of. Of course, you can join this one and this one. In one of the JASA papers by Reich, they also consider type 4. To keep things simple, I did not consider that in this talk. So you have an adjacency matrix where you consider all the sites 168, and for each site you can build up correlation or your set of neighbors for each of the site. Now, what is the interpretation of a Carr model? This is what it is doing. That the conditional distribution of mu is given mu is prime now is again a normal distribution, not with the mean of the neighbors, but an attenuated mean. So that's what the term rho I is coming from, the rho I times mu I bar is. It gives you a very nice representation, and then the variance structure is not tau y squared, but tau I squared divided by ms, where ms denotes the number of main neighbors. So you can see that the more neighbors you have, it will have an influence on the variance of the spatial structure, and then it will also influence the rho I, because now you have the mean to be rho or rho I times mu I bar is. If there is no association, then the mean would be just mu I bar. I mean, basically, if you do not consider that, then you're just taking the mean of your neighbors to be the real name, to the mean for this conditional distribution. So rho controls the degree of spatial association, and tau is the magnitude of variation. So this framework gives us a tool to accommodate if there is any spatial effect for the disease status of one particular site, and whether one particular site might be influencing the status of a set of neighboring sites. Now again, this is deterministic. I mean, you can think of your own set of neighbors. I mean, I chose this discussing with the clinicians there, and they thought that you can start with that. I mean, you can argue that why are you considering only 2? You can go beyond a little more. Definitely you can do that, and your inference will be based on what you assume. Now, what to do with the model for the presence-absence? To account for the informative presence-absence, this is a binary indicator again, like the BOP. We allow the latent factor mu is to predict the locations as well. So we are going into a shared random effects framework. So that you'll soon see in a minute that's what I'm getting to. So if you denote yi not star t to be the indicator if the tooth T is absent for subject I, then again doing the same probic trick, you can get to this model. Now, one thing I want to cite here is that, see, the missingness is happening at the tooth level. So if the tooth is missing, then all the sites you cannot measure, but the response is at the surface level. So in order to, any of a spatial random effect mu I is, so in order to play with the spatial, like the shared random effect structure, you have to. I thought of doing this trick that you can convert yi not t into the zt transpose mu I. That's the same mu I am using for that model. And then what is zt transpose mu I? It is the mean of mu I at the 6 locations for tooth T. Because your missingness is happening at the tooth level, but your response is happening. Your response is at the site level. So you got to combine that in the shared framework. And A0 and B0 are the latent processes relating to the tooth absence indicator. How do you interpret them? So we simultaneously model the observations and their presence absence, and so we believe that both inform about the posteriors of mu and beta, which we want to derive. And if B0 is more than 0, then the unhealthy sites are more likely to be absent. This is what we want to figure out in the factoring in the model. B0 is 0, which means the latent factor is independent of the location of missing tooth. So then you can think of a MCAR model if you think about the missingness structure. Now, interestingly, I would like to state here that it's very hard to show, even it is almost impossible to show that whether you would like to do a missing at random or missing not at random framework in a data set. In a recent paper by Molenbergs published in GRSSB, I think it's GRSSB, he had shown that for every missing at random, there is a missing not at random with equal fit. So it depends on what type of, it depends highly on the assumption, and you cannot really prove that whether the absence of the missingness is really due to at random or not at random. So we go, I am taking a missing not at random route here, but in some plots I would like to show you that probably that is what it is happening, because there is no right way to show it. I mean, they are equivalent. Very interesting work. I would refer that you can go through it. Now, when you introduce these factor models, there is obvious concerns of identifiability. So, because if you integrate over mu I, then you get these moment expressions. So what we did was, you can fix. There are many ways to do it. So what identifiability means is that if you have these expressions, then if you have a factor here, say bj, and then look at this term, then if you have a scalar quantity here as well as scalar quantity below tau, so then alpha times bj, and then tau I squared divided by alpha, if you have all these quantities, then those alpha cancels and you end up with the same kind of covariant structure and mean structure. So it looks like there can be issues. There are always issues with identifiability when you introduce factor models. A good way to do is that you fix b1 equals to 1, so I assume CAL has a fixed slope. And no matter, I would like to also see what are the values of how is CAL correlated with pocket depth as well as bleeding on probing. And doing that, it will identify beta via the mean of fast response and the variance via the variance of the fast response. Now again, there are issues with rho, because if your rho has to lie in between that interval. The lambda 1 and lambda 2 are the smallest and largest eigenvalues of this decomposition. Now if it falls out, then there will be issues with the inverting the matrix when you assume the car structure. Best et al. Recommends a uniform prior on rho. I'm here choosing a beta 1 1. I did different types of priors and I checked some literature. It looks like they are recommending something uniform 0.1 or a little bit something uniform 0.95, that sort of prior, so that things are stabilized when you want to run these models. Now, this is a Bayesian talk, so I have to introduce priors that I'm using. Of course, I will validate those through sensitivity analysis later on. AJ, BJ, and beta have vague normal priors. Sigma ij square are usual inverse gammas. Rho I is beta 1 1, which is also uniform 0 1. Now the hyperparameters Cj, Dj, EF are non-informative gamma. We take these choices of gamma. Now the reason behind choosing is that it is conjugate, leads to very easy coding and tuning, and also what I can do has to have some appeal to the clinical people. Just a little bit about how I'm doing the sampling. Rho is usually Metropolis Hastings from beta. This is the candidate distribution. The latent variables BOP are updated from the truncated full conditionals. Mu I, alpha, beta, all these have conjugate posteriors. CJ, DJ, EF are again Metropolis Hastings with Gaussian candidate. I put the full conditionals in the paper, it's not here. Now MCMC sampling can be carried out using R or Winbugs that just now mentioned. Convergence is reached at 5,000, and then you discard the 5,000 samples and then you do your inference based on the 15,000. And I assess convergence using trace, ACF plots, and Gelman-Rubin diagnostics. If you believe that these are good tools to assess convergence, and these are pretty standard, people use that most of the time. Now I would like to now focus on our primary interest in the subject level parameters beta, like the fixed F fixed. And I would like to know that which part of the mouth or which part of the oral region, which sites are providing what type of information for the estimation of beta. So is it like how are the molars doing, how are the premolars doing, back of the mouth, front part of the mouth? And they would not be providing similar information for the estimation of beta. So I assume that all the responses are Gaussian. So you can think of pocket depth or attachment loss, and with no absent teeth and no spatial covariates. So if you integrate out the latent effect mu I and condition on sigma ij square tau I, rho I, aj, bj, you get these expressions that the expected value of beta is this and the covariance of beta looks like this. So what I get is the posterior of beta is nothing but a weighted linear regression with each subject contributing to the scalar response zi and weighted according to wi. So I have every subject zi, which is made up of the type of response you can think about, and then each has some weights wi. So that weights are highly varying. Though that I want to explore. What are the expression for the weights are? This is the expression of the weight and the expression of delta I. So what it means is that the weight decreases with increasing rho and tau and increases with delta I. I'm going to show some plots. Let's do some plots. So here on the x-axis are my rows, the spatial association going from 0 to 1, and on wi on the left, on the y-axis, you can see that the weight decreases with rho and tau and increases with delta. So what it means basically is that the subjects with little spatial association and small variances and tau and sigma have the most influence on beta's posterior. So as rho increases, you can see that the weight is decreasing, and this one is in the lowest where delta is 1 and tau is 2. Now when delta is 2 and